Hello guys, this is Paul McWhorter with TopTechBoy.com, and we're here today with episode number 97 in our incredible new tutorial series where you are unleashing the power of your Raspberry Pi Pico W. What I will need you to do is pour yourself a nice tall glass of ice cold coffee. That would be straight up black coffee poured over ice. No sugar, no sweeteners, none needed. And as you're pouring your coffee, as always, I want to give a shout out to our friends over at SunFounder. SunFounder is actually sponsoring this most excellent series of video lessons, and in this class, we will be using the Kepler kit for Raspberry Pi Pico W. Now, hopefully most of you guys already have your kit, but if you don't, take a look down in the description. There is a link over to Amazon, and you can hop on over there and pick your kit up. And believe me, your life and my life are going to be a whole lot easier if we are working on identical hardware. But enough of this shameless self-promotion. Let's jump in and talk about what I am going to teach you today. Now, let's go back and look at what we've done in the last 7 or 8 lessons. We've been learning how to program the state machines on the Raspberry Pi Pico W, and we've learned how to interact with and program those state machines. Now, what are the state machines useful for? They're useful for applications that require very precise timing. So now today I want to start getting into an actual application that really does depend on very precise timing. And so what we're going to do is we're going to look at the timing sequences that are necessary in order to control a servo. Now, I know a lot of times you can just run out and grab a library to do servo control where they've already done the heavy lifting for you. But let's say you wanted more custom control of your servo and you want to go in and control it and interact with it more at the bare silicon level. And so we're going to start looking at that today. So today what we're going to do is we're going to look to understand how a servo is actually controlled. And then after that, what we're going to do is next week, we're going to go in, and this will be a homework assignment where you incorporate or you build the basis of a servo control program using the state machine. But today I'll just be showing you what the actual required timing sequence will be. Does that sound good? I hope it does. So let's come over here. Let me start by just kind of showing you what our setup is. Probably be good if I get out of your way. We've got from the Kepler kit, the SunFounder kit, what we've got is the SG90 servo. It's a small servo, and it's a servo that you can safely power off the Raspberry Pi Pico W. We've got the red connection of the servo going to the 5 volts. Now this is something that you got to kind of look at a little bit carefully. And what this is, I am using physical pin 40. That is that pin in the corner. And what that does is that brings in the voltage from the USB. So at this pin 40, you're getting about 5 volts. Now, if we use physical pin 36 over here, physical pin 36 will generate 3.3 volts. Now, some people say that you can run the servo at 3.3 volts. I find that it doesn't necessarily work that well. So instead of connecting it to physical pin 36, I'm going to connect it to physical pin 40. Then the ground, which is the black wire, I have that going to my ground rail. And then the control wire, which is the orange wire, I have going to GPIO pin 20. So you can go ahead and hook your servo up like that. But before we jump in and start coding, we need to go in and kind of map things out. We need to look on paper how these servos are controlled. And so we're going to come over here to our sketchpad view, and we're going to see if we can just really come in and sort of draw up how these servos work. So servos work on, they move to a given position based on the width of a pulse that we apply to the orange line. Okay, now it's a very sort of precise pulse train that it wants. It wants the period of the pulse train to be 20 milliseconds. Okay, so I should probably come up here and write that down. What we should have is in our pulse train, we should have a period of 20 milliseconds. So whatever we do, we're going to repeat it every 20 milliseconds. Now, this is the way you control the position of the servo. That if you have a pulse width of 0.5 milliseconds, a 0.5 millisecond pulse width, that will give you an angle of 0 degrees on the servo. If you have a pulse width of 2.5 milliseconds, that will give you a servo position of 180. And the servo position will scale linearly between 0 and 180 by having a pulse width of between 0.5 milliseconds and 2.5 milliseconds, okay? So what if we wanted a 90-degree deflection? Then what would we want? We would want a 1.5 millisecond because 1.5 is halfway between 0.5 and 2.5. And so hopefully that makes sense. So how would this look? All right. Well, we're going to come over here and we're going to have a period of what? 20 milliseconds. So this would be 5, 10, 15, 20 milliseconds on the x-axis. All right. And then what would we want? Well, if we wanted a 0-degree deflection, we would then need a what? A half-second pulse, a half millisecond pulse. And then we would come out here to 20 milliseconds, and then we would give it that half millisecond pulse again. And this would then give us a deflection of 0 degrees. All right, well, what if we came over here, and if we wanted 90 degrees, we would need to have a pulse width of 1.5 milliseconds. Again, this is 5, 10, 15, 20. And you can see that each minor tick here is 1 millisecond. So this would be 1.5 milliseconds. That would give me a 90-degree deflection. And then finally, we could come here and illustrate that if we wanted a 180-degree deflection or position, we would need 2.5 milliseconds. So again, this is 5, 10, 15, 20. So it's sort of like all the action is happening between a half a millisecond. All the action is happening between a half millisecond and 2.5 milliseconds. Now, since we really want to be dealing in integers, I don't want to be doing this work in milliseconds. I want to be doing the work in microseconds. And so there are 1,000 microseconds in a millisecond. So to convert from milliseconds to microseconds, we multiply by 1,000. So what would I get? And also what I should probably say is, right, I need to come up with a linear equation, but I really just need 2 data points. And so I'll pick these 2 data points. You can pick whichever one you want, but I'll use those 2 and I'm going to convert those to microseconds. And so what I'm going to say is the 0.5 milliseconds would be 500 microseconds, and that would give us 0 degrees. And then if I have 2,500 microseconds, that would give me 180 degrees. Now, what you have to figure out is if we're going to do a line, what is the dependent variable and what is the independent variable? Well, what do I start with? I start with the angle that I want. I start with the angle that I want, and then from that, I need to calculate what the pulse width should be. So I start with the angle and I calculate the pulse width. So the independent variable is going to be the angle, and then the pulse width will be the dependent variable. And we can also think of that as x and y. Angle is our x, and then we calculate y, which is going to be our pulse width. And so what are our 2 points, knowing that what did we just say? That the angle is going to be our x value and the microseconds is going to be our y value. Well, our first point is going to be, if I want an angle of 0, I need to apply 500 microsecond pulse width. And our second point is going to be, if I want 180 degrees, if I want 180 degrees, I need to apply a 2,500 microsecond pulse. Now, in order to get the equation of a line, I need to calculate the slope. Slope is y2 minus y1 over x2 minus x1. Now, the slope is going to become y2 over here, which is 2,500 minus 500 over here. And then we're going to put that over 180 minus 0. And therefore, the slope is going to be, very simply, the slope is going to be 2,000 over 180. All right. Now, what else do we know? The equation of a line, y minus y1 is equal to m onto x minus x1, like that. And so we're going to have y, excuse me, y minus y1, which is 500, is going to be equal to m, which is 2,000 over 180, onto x minus x1. x1 is 0, so this will just be x. And then this is going to become y minus 500 is equal to 2,000 over 180 times x. We're almost there. And now we move the 500 over. We add 500 to both sides of the equation. Y is equal to 2,000 over 180 times x plus 500. Now, what I like to do is I like to go ahead and now convert this to the variables that we are going to be using. And so what I will just say here is that my pulse width, PW, is going to be equal to 2,000 over 180 times my angle, the angle that I want, plus 500. Now, what does this do? What does this do? This takes the angle that I want and it calculates the pulse width that I should apply to get that angle. And so I hope you guys see that math is your friend. And this is really most of the heavy lifting in getting this thing to work. So I hope you guys will write this equation down, and then we'll jump over and we'll start coding this thing up. Okay, we're going to jump over and we're going to start coding this thing up. So let's see if I can come over here to my code view. And we've already talked about how we have the, connections on the circuit. So we've got that taken care of. And so now I think we are just ready to start coding. All right, so what's the first thing? We're going to be doing some timing. We're going to be doing some timing with this program. So right off the bat, we better import the time library. So we're going to import time. And remember, I'm just going to show you this using Python, and then you're going to know that the better solution is going to be the state machine, which will be your homework assignment. But I can't really give you the homework assignment if you don't really understand how the servo works. So now we're going to say from machine import pin, like that. Then I'm going to say servo pin is equal to pin, the method. What pin did I say we were on? GPIO pin 20, and it is going to be a pin dot out, like that. Okay. Now what we're going to do is we're going to say while true. When is true true? True is always true. And now I'm just going to say, what angle do I want? Well, let's just say I want an angle of 90 degrees. So I want this servo to go to 90 degrees. Let's say I want this servo to go to 90 degrees, okay? And so what I will need to do is I will need to then come in and I will need to calculate my pulse width. And my pulse width is going to be equal to that equation, the angle that I want, times 2,000 divided by 180 plus 500. All right. Now you know that we want to apply an integer value when we're doing these commands, and so I better go ahead and convert this to an int, because some of these things would not like a floating point. So we're going to round it to the nearest integer by using that command. Now what do we need to do? We need to say that I want the servo pin dot on. I want to turn the servo pin on. Now how long do I want to leave it on for PW? So what I'll say is I'll say time dot sleep in microseconds US, and I want to sleep for PW. Okay, now why are we sleeping in microseconds? Because this equation was derived in microseconds. So since we use microseconds for the equation, we better use microseconds now in the code, if that makes sense. So now that we've been on for that pulse width, we've been on for that, then what do we want to do? I want to time dot sleep. I want to turn off servo pin. So now that I have completed my required pulse width, I'm going to turn servo pin off like that. And now I'm going to time dot sleep. All right. Now let's go, and we probably need to think about that for just a second. Let me come back over here. I probably didn't talk about that quite enough. So let's come back over here and let's look at the sketch pad. There it is. Okay, let's look at the sketch pad. And what do we need to remember? We need to remember that we have a period. We have a period of what? 20 milliseconds. The period is 20 milliseconds. And so what does that mean? That means that the period should be 20,000 microseconds. All right. Now, what you can see though is that if I have already left this on for PW, then how long should I leave it off? How long I should leave it off would be the period minus the pulse width. And so if I leave it on for pulse width and then I leave it off for period minus pulse width, the period will in fact always be the period. And so we want to make sure that we do this, and we know that our period is 20,000 microseconds, so this will be 20,000 minus the pulse width. And that is how long we should then leave this off. Hopefully that makes sense, and I can see that you didn't see everything behind me, but I'll move out of the way so you can see it now. I try not to do that, but it does happen every once in a while. Okay, we're going to come back to our code view now. And so basically that's just to say, how long do we leave this off? The time.sleep underscore microseconds, or US, is going to be the 20,000, which is the total period minus the PW, which we have already left it on. Okay, and then just to kind of help me debug, I'm going to go ahead and print. I'm going to go ahead and print PW, and that way we can see what's going on. Okay, I hope that makes sense. Let's see here. Give me just a second. I need to just do one quick thing here. I need to try to clear this thing out. Okay, I think we got that. All right, just a little bookkeeping stuff there. All right, so that's the program. And then also what I want you guys to see, I'll show you that in just, I'll go ahead and show you. Okay, so I'm going to come over here. And what you can see is on my circuit, like I said, this is connected to pin 20, like I told you. But then I also have this hooked up to my oscilloscope. So I'm looking at pin 20 in the oscilloscope, and what I want to see is I want to see what signal I get on the oscilloscope, and then I want to see what angle that I get on the servo. Now, what we said over here in the code is, we want to go to 90 degrees, and then that should calculate a pulse width of 1,500. So what should we see printed out? The pulse width should be 1,500. And then what we should see is we should see this servo go to 90 degrees. So let's check that out. So I'm going to go ahead and run it, and boom. What do you see? What do you see? And I got to fix this a little bit, and then we can talk about it. Okay, let's see here. This is a little... Actually, I got a little bit of a glitch here in my oscilloscope, which I'm wanting to show you. I want to show you the oscilloscope working, though. Okay, we'll look at the oscilloscope in a minute. But what I want you to see is this went to 90 degrees, and then it did calculate a pulse width of 1,500. So the math is working right, the code is working right, and the circuit is working right. But let's come over here and let's try 0. Okay, let's try 0 like this, and then we're going to run it. And boom, it went to 0 degrees as we expected. Now let's try 180. Let's try 180 degrees. And then we will come over here and it goes to 180. Let's try 45 degrees. 45 degrees. Let's run it. And then it goes to 45 degrees. Let's try one more. 135 degrees. 135 degrees goes to 135. And then let's just go back to 90 and leave it at 90 because that's kind of nice to see there like that. Okay, to 90. Okay, now I need to get my oscilloscope working here, and maybe I'll let you guys see as I'm fooling with this thing, but I'm really not sure why I'm not getting a good oscilloscope signal here. So I've got it normal. I have it... maybe I need to, it's like I'm not connected. Okay, then you always got to make sure that it is grounded well. You got to have a good ground. So let me come in and make sure that we've got this thing grounded. It's grounded. It's in the right pin. Let's see if I can... Okay, there it is. So what had happened was it was auto-scaling. Ah, beautiful. Why were you not seeing this? It was auto-scaling and you were just looking at this noise down here. And that really, really confused me. Okay, so first of all, at 90 degrees, what pulse width did we apply to get 90 degrees? We applied 1,500 microseconds. So now we have to ask ourselves, are we getting a 1,500 microsecond pulse? So we're going to come over here and we're going to look at this pulse, and let's go down to a smaller value. Okay, and this is saying that it is 500 microseconds per division, and I have 1, 2, 3 divisions, so I'm getting the 1,500 microseconds that I wanted. But now let's look at the whole period. Well, I've got to come in on this to get the whole period. Let's see if I can do it this way and move it over. And you guys, you can do these lessons without an oscilloscope, but if you want to get this oscilloscope and it'll really kind of help you see what's going on with your timing when we're doing the state machine stuff, look down in the description. There's a link over to Amazon where you can get the same oscilloscope that I'm using. But now let's say our period starts here, and I'm going to count the number of divisions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 divisions precisely at 2 milliseconds per division would be 20 milliseconds. So I'm getting the right pulse. I am getting the right period. I'm getting the right calculated pulse width. I'm getting the right measured pulse width, and I am getting the right angle. So the circuit had to work. The math had to work, the programming had to work, everything had to work, and what do we get? We get the right angle on our servo. So that all works really well. Now, why would we not just do things this way? Well, this works pretty well if you just have a very simple program. What is the only thing that I've really done? I've done like a quick calculation that would slow us up a little bit, and then I printed the pulse width. That would slow us up a little bit, but pretty much the timing is defined by these two things. But what if we needed to come in and we needed to wait on data from data input from the user? Or what if we needed to go off and do a more complicated calculation, or go off and do a reading from another component? Then all of a sudden our timing is going to be thrown off, and very, very quickly what you're going to see is the lines of code are going to begin to affect this pulse width. And as the lines of code affect the pulse width, it's then going to start leading to jitter, or little vibrations in our servo. And so I've done this program in Python to show you how the timing works, but you can see that Python really has very, very poor timing. And also Python sometimes just comes in and says, okay, I'm going to clean my registers, or I'm going to dump my, my buckets or whatever. It goes off and it does maintenance in the middle of running your program. So it is notoriously poor at precise timing. So I did this so you understand the timing that controls the servo, but you can probably now imagine what your homework assignment is going to be. Your homework assignment is going to be to generate these pulses using only the state machine. You're going to generate the pulses using only the state machine. Now, you don't have to have it where the position is controlled by the user. You can just sort of hard program in the pulse width that you want. So you can see I kind of hardwired in the angle, and then from the angle I calculate the pulse width. Well, in the state machine, you can't hardwire in an angle because you can't do math. So at the state machine, you're going to have to kind of hardwire in a pulse width, and you could hardwire in a pulse width that, let's just say, gave you 90 degrees. Okay, so that is your homework assignment. Repeat what I just did using the state machine, hardwiring in a value that would give you 90 degrees, okay? And then you need to post that homework assignment to YouTube. All right, now what I will say is that this isn't very useful, because the state machine is just going and it's going to keep it at a certain angle. And if you wanted to change the angle, then your program's not going to be able to do that. You're going to have to change the program. But I want you to just get that simple baby step done. And what are we moving towards? We're moving towards having a servo library that will work with more than one servo and will work with getting precision pulse widths, no matter what the main Python program is doing. And so that's the direction that we're going. But for starters today, I'm just going to try to get you to generate this pulse train using the state machine, and then applying that pulse train to your servo. I hope that makes sense. And I also hope you guys are having as much fun taking this class as I am making them. What I want to do is I want to, as always, give a shout out to my Patreon supporters. Right now, it is you Patreons that are enabling me to keep making this content. So I want to thank you. It is your support that is the only thing right now that is keeping me in the game. So thank you. You can also help me by giving me a thumbs up and leaving a comment down below. If you haven't already subscribed to the channel, when you do, make sure you ring that bell so you'll get notifications when future lessons drop. And most importantly, share this video with other people, because the world needs more people doing engineering and fewer people sitting around watching silly cat videos. Paul McWhorter with TopTechBoy.com. I will talk to you guys later.